Okay, so I'm going to present myself. I'm José Peña. I'm an astronomy student in the PhD program of Universidad de Chile, and I work with asteroids. And I'm just starting to use the ALeRCE database to query for asteroids and looking for asteroids. So I'm going to show you pretty much the basic things I have been doing with this. So in the first part, we're going to look for asteroids. We're going to ask for asteroids to the ALeRCE database. And for that, we need to install the ALeRCE client. So we just have to run this cell, this line. We run it, we wait for it to install it, and we will be able to use it. Okay, so we have it now. Now we're going to load some libraries. Maybe the most important one is pandas. And we also use a lot of AstroPy and some matplotlib to plot figures. So more libraries. This to ask ALeRCE, and we declare the client of ALeRCE. I'm not going to use it just yet, but at the end of the notebook, I will use the client. So we need some credentials. The credentials are in this direction. And now I connect to the database. And now I'm connected to the database. The database contains these tables. And the ones we are going to use here is the table object and the table probability. And maybe the table detections, I don't remember very well. So the first query to the database will be for the tables. What tables are in the database? And are all of these tables like the ones I just showed you and others? And now we can see what columns are in each table. So we know what to ask to what table. So in the reference table, there are all these columns, etc. Now we're going to query to ALeRCE for all the objects between January 1st and February 1st with at most one detection and that are classified as asteroids with the stamp classifier. So if it's an asteroid, it means they appear only once in one position because asteroids move. So that's the reason we are asking these detections to have only one, to these objects to have only one detection. And the probability of 0.7, like that's a high probability of being actually an asteroid. So we use the AstroPy time functionality with the MJD because the dates in these tables are in MJDs. And this is the table. So we select the OID, that's an identifier of the object, the mean right ascension and the mean declination, because one object with one OID can have multiple observations. So we are asking for the mean right ascension and the mean declination. But because they are asteroids, they have only one detection, and we demanded to have only one detection. So it's the mean of one data point. And the first MJD is the same of last MJD because there is only one. And we join this table object with the table probability because we want them to have certain probability of 0.7 or more and be classified as an asteroid. So we run this cell. Here we the first MJD is higher or lower than the last first MJD we declare here. So we do the query and we load the answer as a pandas table called ask. And now we have the ask state that looks like this. So we have a column with the right ascension, the declination, the MJD, and the number of detections that all of them must be 1 because we declare it that way. So we have this table of asteroids or candidates to be an asteroid, but we have in ALeRCE, we have a cross match with MPC, the Minor Planet Center, and they send these detections to the MPC and they answer if they are near a known asset. Accordingly to their estimation of those positions of the known asteroids. So we ask that information is the SS that ZTF, like SS for solar system, and where OID is in a list of OIDs that come from this table. So we take all the OIDs on this table and we put them in a list, and if an object in the solar system ZTF appear with the same OID, we select it. And the same as before, to a pandas table called SS. And that's how it looks like. So we have the OID that is, these OIDs are inside like a set of these OIDs. They have a candidate, like a candidate ID. This candidate ID is actually unique, as I understand, because one OID refers to objects that are found in the same position in the sky. But if you find several times in the same position, they have different OID. They have different candidate, but the same OID. Now in this table, they give us the distance in arc seconds to a known asteroid, solar system distance to the nearest, and then the magnitude of that nearest asteroid, and the name. So in the name we have, like, in general, we have a number because asteroids, known asteroids generally have just a number as a name. So we plot the distribution of separation of these objects with the cross match in MPC. So we are going to plot an histogram of this column. So we tell them the distance to be higher than 0 because there are some distance that are like -99. That is probably because they don't have anything to match that object. And this is how it looks like. So we have many bodies around 0 and 5 arc seconds. And then we have a few more. I don't know if to consider bodies farther away than 10 arc seconds, like actual cross match. But and that's the distance to the nearest. And now we have all these positions in equatorial coordinates, but ecliptic coordinates is a more convenient frame for solar system bodies. So we change them with this sky code that is from AstroPy. So we give them the mean rad, mean dec. We tell them the unit is degrees, and the frame is ALeRCE, which is not exactly true because ALeRCE is in the center of the solar system, and this is from the observer in the Earth. But the only thing we want to do is to rotate the coordinates from equatorial to ecliptic. And that's the only thing these things do. So it thinks it's from the solar system barycenter, but it is not, but it doesn't matter because we only want a rotation, a geometric rotation. And we create these two other columns to the table AST with the ecliptic latitude and the ecliptic longitude. And we plot an histogram of latitudes, and we can see pretty much all the bodies found during January are near the ecliptic, plus minus 20 degrees. And we plot them using data shader because it looks nice. For that, we need to install data shader. So we install it and then we import it. And we finally plot it. And this is how it looks like. And there you can see how to plot with data shader. So most of them are near the ecliptic. You can see in here some higher densities. That's more because of the cadence of the survey, not because there are actually more objects in this area, just because it is more observed. And now we are going to look how these known bodies look like in our database, like how many times they are detected. And we can see most of them are detected only twice, and only a few of them are detected more than 10 times. And for that, we created a new table that is called NDET. And NDET has two columns with the name of the body and the number of times it was detected by CERTIA. And this is how we created it. So we make a group by the name, and we apply a function for each of them that gives the shape, the first dimension of the shape, meaning the length, how many detections. And so we are going to plot all of the bodies with 9 or more detections in equatorial and in ecliptic coordinates. So we iterate for the index, that is the name of the table NDET. And we make some mask to get the OIDs of those bodies and where those OIDs appear in the AST table. So we plot the positions from the asteroid. And this is how it looks like. So you can see they have very interesting shapes. And we believe this is because when we go to bodies with a high number of detections, those high number of detections comes probably because they are doing some weird apparent movement in the sky that make them appear many times because they are like around the same field of view, in the same field of view. Wait, I don't know what happened. So we are going to study the body with the most detections, and that's the number of the body. So the best asteroids, like the best because it has more number of detections, is very simple way to get it, IDX max, and that's the name of the body. So we plot how it looked like in ecliptic and equatorial coordinates, and you can see this like it's not a straight line, it's a little bit curved. So what interesting thing can we do with this body? We can query for their magnitudes, heat magnitudes, and plot a light curve. Now, light curves are very important, or getting magnitudes is very important because we can get light curves, but we can also get colors. We can get a distance or sizes of the body. We know the distance, so it's useful for a lot of important stuff in the asteroid analysis. So the same way we did before for the cross match, we are going to look for the OIDs in the AST table for the OIDs of the non-body, and we are asking for those OIDs in the table detection, and the table detections has these columns. And this is how it looked like in here. Let's do the query. And so we have the OIDs, the MJD, the filter ID. If it is 1, it means that it was observed with the G band. And if it is 2, it was made the observation with the R band. The magnitude, the aperture magnitude, the sigma of that magnitude, like the error, and if we have a stamp for that asteroid, and it says all of the detections has a stamp, and we have all of these magnitudes. These magnitudes are the ZTF magnitudes, but before we had some magnitudes from the cross match, and these are magnitudes accordingly to MPC. So MPC makes an estimation of the position, and it also estimates the magnitude of that body at that position in that time. So we plot the predicted light curve by MPC using those magnitudes from the cross match, and we compare it with the observed light curve. So we get the magnitude from the MPC using that mask. Then we extract the MJD's magnitudes from the table detections, the table we just downloaded. And we make some mask for the G band and the R band, so we can plot them separately. So we can see accordingly to MPC, the asteroid is getting brighter with time, and we can see the same with the ZTF magnitudes. Of course, there is a color shift. but we can see the variation is around 0.5 magnitudes, that it is similar to the variation accordingly to NPC. Now maybe you are not satisfied with the photometry by NPC. You want to make your own photometry, or maybe you want to observe the image itself to get some morphological characterizations that maybe if you are looking for comets or for near-Earth objects, that can be important. Or maybe you just want to make a GIF, like a little movie of your detections. For all of that, you need the stamps. So we're going to use the client of ALeRCE we declared at the beginning. And for the OIDs of the known body, we're going to plot all the stamps. Oh, there is a breaking here. Let's comment that. And now we have all the stamps. So with this query, when we use the client and its function get stamps, we use the OID of the body, but it returns an array of the stamps. These stamps are like feeds-like images, so we can use them the same way you open a feeds file with AstroPy. You use the same in here, and it gives you three stamps. One stamp the science, another the reference, another the difference. So the science is like the actual image. In here you see in the center the asteroid. In the reference, you see nothing. So it is most likely an asteroid. And it makes sense because it was recognized as a known asteroid. And the difference between these two. And then you can see only the asteroid. You don't see the other stars. And everything goes right. And then there was an error in here. The file wasn't found, although the table said all the detections had a stamp. Apparently that is not true, so you must be aware of that kind of thing, because it can give you errors in your code. That's why I use try. And now we can also get the ephemeris. So in this case, it doesn't make much sense to get ephemeris because we have the cross match with the NPC, but that is not going to be always true. Maybe for another surveys that ALeRCE will work, or you in your own projects will work, you won't have that. And you may want to get your own ephemeris to do your own cross match. And I've been working in something like that. I call it ALERCE, like ALeRCE ephemeris, and it's under construction. But in here, I can show you a preview. So from ALERCE, you import a class called query, and in the query, you can query like a field of view with a center that is a coordinate, a radius, an epoch that is the time you are using. That is a time class from AstroPy, an observer that is also an AstroPy observer. And in this case, I state that it looks only for the number of the body. So if you don't put anything in here, it will ask for all the hundreds of known asteroids and it will take many minutes. But in here, I only ask for one. So it is inspired on another AstroPy code for querying and the EMCCE. That is a very good ephemeris, public ephemeris service. And I'm going to show you the comparison of my code with that one. So because it is under construction, I cannot run it in Colab because it is not for to be installed in this space. But you can get these sample coordinates from this direction, this link, and the course of ZTF from table asked. And in here, because the cores are SkyCore kind of cores, we can use the SkyCore utility separation that gives you the distance between one coordinate and another, and to plot it in arcseconds. So you can see the difference between my estimation, my ephemeris, and the actual detection of ZTF is very small, less than 1 arcsecond. Is the worst estimation is 0.2 arcseconds. You can plot it in here. So in here you have in red dots the ZTF, and in crosses my estimation, and it looks pretty good. And here I compare it with my work with other public services. So the public service of the MPC is pretty bad. It gives error of around 6 or 7 arcseconds, and it only allows time precisions of 0.01 days. So that's very inaccurate. But the EMCCE, the one I was telling you before, this is the error. It's a very small error, less than 1 arcsecond, but it's a little bit biased. And this is my work. The Aleph errors are small, a little bit smaller than the MCC errors, and they are not biased. And this is, I'm not sure why they are biased, but I'm using pretty much the same technique, that it is to use not only the sun gravity, but adding the gravity of all the other planets. So hopefully this will be available at some time. I don't know if as a public service for ALeRCE or like a public Python package. And that's it. I hope you were able to see how to download data from ALeRCE for asteroids and getting some important stuff like the magnitudes. I don't know if you have any questions.
Oh, thank you, Jose. We have 10 minutes until the end of this session. So maybe if anyone can have a question, just ask directly. You can unmute your microphone and ask to Jose Peña directly, please.
There's any question or any doubt?
Yes, hello.
Yes, I hear you.
Hello, Jose. I'm Alvaro Valenzuela. I want to ask you about if you can cross-match these alerts with other databases of known asteroids. I'm thinking on the potential hazardous asteroids, if you can compute if they are hazardous or something. I don't know if you've tried that.
Yes, there is, as far as I know, for asteroids, they only ask to the MPC. But if you go to the table, when we get all the table names, we have in here ALeRCE, Gaia ZTF, PS1 ZTF, and Solar System ZTF. This is the one we use, and this is with MPC. I almost sure the other ones, the one with WISE or PS1, they are not cross-matching asteroids, I suppose. Gaia, well, Gaia is only stars, so that's a cross match for stars. So I'm not sure if there are other cross matches. And the other thing is that we receive these alerts from ZTF, but they have their own filter. They have their own project of catching these hazardous asteroids. So it's unlikely that they will give ALeRCE those detections because they keep them for themselves because it is their own project. So that's one of the reasons I was trying to build my own ephemeris service to do this cross match by myself, if not with ZTF, but for the surveys to come. I don't know if that answers your question.
Yes, yes, clearly. Thank you.
So, another question? Well, maybe a few comments, a few final comments. It is very important for you, I think, if you want to use ZTF to understand a little bit of the SQL grammar. I don't know how to say it. SQL language. It is very, very simple. It works like this, and you can use it in pandas. Like it's the future for data frames. And another thing is to, if you are going to use ALeRCE, try to be careful with the amount of data you are asking. And if you are making a big query, a good advice would be for you to save it, like not leave it just in memory, like save it in your hard drive, so you don't have to make the query many times to get the same data. You can just look for the data you save. That's it. I don't know if you have any other question.
No more questions? Anyone? Maybe I also want to add that you can request or query the database through the API, through the client. So you have both alternatives. You can query through the SQL language, but also through the API, the client that is so there are some queries that will be easier in the API. So we are at the end of this
yes, section. I have a question in here. Another question. So Felipe Gran is asking me if we can misidentify these alerts with hypervelocity stars. I'm not so sure how fast hypervelocity stars can be. So I suppose it is possible, but that is also why we are using the probability machine learning stuff to identify asteroids from stars, from supernovae, etc., etc. That's also giving you a good probability of actually being an asteroid. And another thing to remark is you can still have the cross match with other databases like Gaia. So maybe if you know that this hypervelocity star is in Gaia, you can do the cross match, and if it is cross matched with that star in Gaia, then you could say it is not an asteroid, it's an hypervelocity star. I think that's all.
Okay, thank you very much, Jose. I encourage you to go to the next parallel sessions. One will be about variable stars and another about AGNs, and it will start in 15 and 3:15. So we will see you then. Thank you very much.
Thank you, guys. Goodbye.